In the arid heart of the ancient supercontinent Pangaea, thousands of kilometers from the ocean, a pivotal moment in Earth's history was unfolding. It was at that precise instant that the first drops of rain began to fall. Not far from Pangaea's western coast, what we now know as Canada, massive volcanic activity triggered a series of events that made this deluge inevitable. But this was no ordinary passing storm. It marked the beginning of an unrelenting reign that would last over 1,000,000 years, reshaping the course of life and setting the stage for dinosaurs to rise in a true evolutionary conquest. What's most surprising is that such phenomena are usually among the most powerful and reliable triggers of mass extinctions on the planet. But this time, it was different, pushing the concept of the butterfly effect to its limits. Imagine, if the flap of a butterfly's wings can create a tornado thousands of kilometers away, what could an eruption 100 times greater than a supervolcano cause? Join me as we uncover how an extinction event 230 million years ago increased life's diversity on Earth and accelerated the evolution of dinosaurs. We'll explore how, through Earth's natural cycles, the release of ancient gases contributed to climate change long before the Industrial Revolution. Pangaea was, without a doubt, the largest continent to ever exist in Earth's history, a record difficult to surpass as it was essentially the union of all modern continents. Its vast expanse meant that its center was far removed from coastal climates, receiving very little rain and favoring the evolution of species that required less water to survive. During this dry period, around 300 million years ago in the Carboniferous, several species emerged that remain vital to this day, such as dragonflies, millipedes, and spiders. This period also saw an explosion of diapsids, a group that includes lizards and snakes, as well as archosaurs. The name might not ring a bell, but you're certainly familiar with some of their descendants, crocodiles, birds, and later dinosaurs. But we'll return to them later. Ancient Earth was a chaotic and brutal place, with constant threats at every turn. The dangers weren't confined to the surface, they also lurked in the depths where the true risks lay hidden. While meteorites capture public attention, the answers to the million-year storm that transformed the planet lie beneath Earth's crust. Life as we know it exists on an incredibly thin layer of Earth's surface. If the planet were represented as a full collection of stories, the layer that sustains all known life would occupy just a few paragraphs on a single page. Beneath that layer, massive columns of heat rise from the core, expanding like mushrooms as they ascend and push searing magma against the thin crust. These columns pierce the crust wherever they find a way through, unconstrained by continental fault lines like those in the Pacific Ring of Fire, where most modern volcanic activity is concentrated. These plumes can release magma onto the surface for over 1,000,000 years in events known as flood basalt eruptions, which are linked to the most severe extinction events in Earth's history, including the Great Dying, when ocean temperatures soared to 40 degrees Celsius. Despite life's incredible resilience, it's estimated that over 99% of all species that have ever existed on Earth have gone extinct. After all, it's impossible to evolve fast enough to escape a giant asteroid hurtling at 20 kilometers per second. Yet these volcanic processes, though slower and less dramatic, can cause even greater devastation over time. Evidence of this flood volcanism can be found scattered across the globe. These basaltic eruptions have created immense land formations, such as the Siberian Traps in Russia, the Deccan Traps in India, and the Rangelia Large Igneous Province in Canada and Alaska. These are vast expanses of cooled basaltic rock, several kilometers deep, making them 100 times larger than supervolcanoes. Are you enjoying what you're watching? If so, consider subscribing to the channel. It really helps me keep creating content like this for you. It costs you nothing, and it motivates me a lot to keep making more videos. So if you want to support the channel, go ahead and subscribe, and don't forget to hit the bell so you don't miss anything. When we date these flood basalts, we find that many of these eruptions coincide with mass extinction events. However, one event doesn't align with the pattern of previous mass extinctions. The rain-triggering event that sparked the so-called Carnian Pluvial episode, or as we might call it, the time it rained for over 1,000,000 years. It's believed that volcanic activity in the Rangelia province was responsible for this incredible transformation. turning an arid desert into an oasis that fueled the explosion of the dinosaurs. So what set the Pangaea eruption apart from others? What made it different? One thing is clear. In this case, size mattered. While the eruption caused an extinction event, wiping out around 30% of marine species during the Carnian Pluvial episode, its magnitude turned out to be ideal for sparking a net increase in life on Earth. Overall, biodiversity remained relatively stable because extinctions were offset by the emergence of new and remarkable species, better adapted to a wetter world. Instead of an extinction event, this was more of a reinvention phase for life on Earth. But how could such a slow eruption provoke such a profound change in the climate? To understand how this transformative event reshaped life on Earth, let's consider a phenomenon we are all too familiar with today: climate change, particularly the release of stored carbon dioxide and methane. Eruptions like this not only release carbon dioxide from Earth's mantle, but can also trigger its release from other sources, including deposits we once thought were influenced solely by humans, ancient fossil fuel reserves. You're probably familiar with the fire triangle: fuel, heat, and oxygen, which helps explain this process. Imagine introducing magma at 600 degrees to the base of intact coal seams. It's like sparking a barrel of gunpowder. The combustion of these raw coal beds would have released incredible amounts of particles and greenhouse gases, both critical for driving cloud formation and rain. Just as we see today, the increase in greenhouse gases trap more energy from the sun. And where does that energy go? Earth's systems redistribute it, with the water cycle being the primary absorber of this excess energy, becoming supercharged in the process. The sun's energy is absorbed by the land and sea, evaporating water from the surface. Once in the atmosphere, this water can travel vast distances before precipitating back onto the land and returning to the sea in an endless cycle. The more energy trapped by greenhouse gases, the faster the water cycle spins. Flood basalt eruptions illustrate the extreme interplay between three of Earth's fundamental cycles: the geological cycle, the carbon cycle, and the water cycle. The formation of Pangaia's vast igneous province would have released enormous amounts of CO2, pushing atmospheric levels beyond 1,000 ppm, parts per million. For reference, ppm measures the concentration of one substance in a million parts of another. For example, when we say atmospheric CO2 is at 400 ppm, it means 400 out of every million air molecules are CO2. At 1,000 ppm, 2.5 times today's levels, temperatures rose by 3 to 4 degrees. This intensified the water cycle, increasing evaporation and cloud formation, driving rain deeper into Pangaea's interior. During this period, Earth became warmer and wetter, drastically altering its climate. Species adapted to dry, stable conditions before this prolonged rainfall began to face pressure from all sides. In this period of change in Earth's history, traditional ecosystems seemed to collapse as quickly as new niches emerged. The balance was shifting. Moreover, species were not only grappling with temperature changes, but also with shifts in environmental pH. Carbon dioxide wasn't the only gas released during the Pangaea eruption. Hydrogen sulfide was also ejected into the atmosphere. This gas, infamous for its rotten egg smell, reacted with oxygen and water to form sulfuric acid, leading to what we know as acid rain. As this rain fell, its acidity flooded soils and oceans, adding to the environmental stress faced by many species. Interestingly, the geological record of this period, the Carnian, reveals an abundance of amber. This protective resin, produced by trees in times of great stress, suggests that plant life also endured significant challenges during this era. The incredible volume of rain on the supercontinent triggered massive surface water flows. Rushing over the arid terrain, these slightly acidic streams eroded the land as they moved. Some of this acidic water seeped into small cracks in limestone and dolomite rocks, gradually wearing them away. This process transformed the underground landscape, giving rise to intricate cave systems, such as the famous Triassic caves in Britain, carved into Carboniferous limestone in places like Tytherington, Gloucestershire. These new caves not only became impressive formations, but also provided unique and previously unknown habitats where life found new opportunities to adapt and thrive. Over time, the flow of acidic, mineral-rich water reached the ocean, carrying eroded rock and mineral fragments, altering coastal ecosystems and pushing them into unprecedented environments. The impact on ocean species was devastating. Vast areas of the ocean became anoxic, deprived of oxygen, and highly acidic, creating extremely hostile conditions for existing marine ecosystems. Among the most affected were conodonts, ammonoids, crinoids, and certain green algae, all vital links in the marine food chain. At the same time, some life forms managed to adapt. Dinoflagellates, which are essential components of today's plankton, thrived and began to establish themselves as key players in the ocean's survival. This shift in species demonstrates how, in times of crisis, life finds unexpected pathways and evolves into new forms of existence. While the oceans endured these extreme conditions, a new kind of life was beginning to emerge and flourish on land. One of the earliest known dinosaurs, the majestic Herrerasaurus, was adapting to these changes. Measuring about 6 meters long and weighing over 300 kilograms, this prehistoric carnivore stood out as one of the largest reptiles of its time, dominating a world still inhabited by smaller creatures. Its home was the Ecological Formation, a vast volcanic floodplain covered in dense jungles located in what is now South America. The region's warm and humid climate provided an ideal habitat for the Herrerasaurus, which was fully adapted to these extreme conditions. When the rains of the Carnian Pluvial episode began, Herrerasaurus was one of the great beneficiaries of these changes. The ecosystems and habitats it already knew expanded, and its usual environment multiplied across Pangaea. As it ventured further inland, it found oases teeming with resources, uncharted zones filled with abundant plants and prey, especially after the extinction of numerous herbivores and other competitors. During this period of prosperity, Herrerasaurus and its contemporaries evolved and thrived, occupying vast and diverse territories. We can imagine the wide variety of landscapes these early dinosaurs roamed, each brimming with opportunities for coevolution with other organisms and shaping the ecological balance of their environments. Elsewhere in what would become Europe, dinosaurs were also beginning to expand. In the Dolomites, these giant reptiles moved in herds across plains, leaving footprints etched into rocks for posterity. During the 3 to 4 million years of the Carnian Pluvial episode, dinosaurs evolved rapidly, transitioning from barely visible in fossil records to dominating the footprints left in sediment. They accounted for more than 90% of the tracks found, a phenomenon consistent with other records across Pangaea, such as in Central Europe and the Ecological Basin in Argentina. This reflects the dinosaurs' rapid expansion and success across the continent. The Carnian Pluvial episode, spanning approximately 2 million years, left a profound mark on Earth's history. With 4 periods of extreme rainfall, each cycle reshaped the landscape, acting as a climatic and ecological reset. To grasp the magnitude of these changes, consider the famous biblical storm of 40 days. In comparison, that storm seems brief, akin to a heavy rainy season. However, the anticipated 5th period of rains never came. As volcanic eruptions in Rangelia subsided, so did emissions of greenhouse gases and acids. The dense vegetation of Pangaea absorbed the remaining carbon dioxide, stabilizing the climate and contributing to the carbon cycle. The remnants of this vegetation eventually became the coal deposits we use today as fossil fuels. Now that we analyze this long and complex period, it answers a profound question about the impact of natural events. If the flap of a butterfly's wings can cause a tornado 1,000 miles away, what effect does a volcanic eruption 100 times larger than a supervolcano have? The answer is as awe-inspiring as it is daunting: a complete terraforming of Earth's land, sea, and air. A total rewriting of life's rules. Thanks to these changes, dinosaurs experienced their golden age, marking the beginning of an era that would last hundreds of millions of years. However, 180 million years after this event, another cataclysm would strike Earth, ending their reign and paving the way for mammals to dominate, including us, humans. These events serve as a powerful reminder that at every turning point, life faces challenges of adaptation and survival, always finding ways to flourish under new rules, constantly reinventing the planet's natural balance.